In this example, let's use S sub 10. In other words, we're going to use 10 subinterval. Remember, the number of subinterval have to be even. S stands for the Simpson approximation, Simpson rule approximation. So we'll use S sub 10 to approximate our integral from 1 to 2, 1 of x dx. Okay, the solution, we'll jump right into it. S sub 10 will be delta x over 3. Well, delta x, remember, we are looking at 2 minus 1 divided by 10, so it's 0.1, so 0.1 over 3. And then here's what we're going to calculate. What is the first value? Well, we'll start with f of 1, and then we'll go into 4, and the next value will be 1.1, right? Each interval is 0.1. The width of each subinterval is 0.1. So 4 times 1.1, and then 2 times f of 1.2, 4 times f of 1.3, and then we'll do our dot, dot, dot thing. And then we'll go to the last 3. So we have 2 f of 1.8 plus 4, the one before last, f of 1.9, and then back to 1, which is f of 2. So we use our calculators, or if we are more sophisticated, we write a little something in Excel, or even we are better than that, then we go and program something, and we calculate, and it comes out as 0.693150. Okay? And if you think about it, this is remarkably close to the actual value. Let me bring the actual value from last time. Those are the results from last time. Okay, if you recall, when we did it we calculated using the trapezoidal rule, but with 5 subintervals. So we know that we get better result when we increase the number of subintervals. But it was 0.691908. Then we used the midpoint. I'm sorry, this was the midpoint, m sub 5. And then we used the trapezoidal rule. We got 0.693. I'm sorry, 0.695635. This is the exact value. The exact value is the natural log of 2, 0.693147. Look how close we are. We are off only in the 6 decimal places by 3 millionth. So this is, and 10 subintervals is nothing, especially if you mechanize the calculation. Even with our graphing calculators, we just can go and use a table and calculate this thing. I would personally, to me, the quickest way to do it is Excel. But again, if you are efficient at programming, then programming would be good too, because you can increase the accuracy by going, if you program, you might as well go ahead and use n equals 100 and get a really good precision. Dane, you want to share something with us? It is pretty accurate. I mean, the Simpson rule is very good. Let me write a couple of comments here in addition to the Simpson, what we have. The Simpson rule really is a weighted average between that combine the midpoint and the trapezoidal. Okay, how it's weighted? Well, it turned out that S of 2n, in other words, we put 2n because we want to guarantee that we have even number of subintervals. It will be one third of the trapezoidal if we use n, half the number of subintervals, and then 2/3 of the midpoint. So if you look at the result that we had before, we use T of 5, M of 5, okay? We would obtain the same result if we took 1/3 of this and 2/3 of that, in this case T5, M5, and then this will be the same result as this one. Because this applies to the Simpson rule when you double the number of subintervals. And that's why I said that we had before M of 5 and T of 5, but now we calculate S of 10. So this is exactly, if you take 1/3 of this and 2/3 of that, you end up having this. For T and for M. And that's what we used last time, 5 and 5. And we compare it to the 10. This is really a side note, because you're not going to calculate two different approximations to get one. You're going to jump and do the Simpson right away.
So it should be T of 5, right? It's written as T of N.
T sub n, right. Example, since you are hard-headed, n equals 5, then S of 10 equals 1/3 T of 5 plus 2/3 M of 5. How about that? That makes sense? Yeah. All right, let me give you one more example, and then we'll move away from this. I'm sorry? Here, oh, I see. I apologize. I'm the hard-headed. No, I'm really the one who doesn't see well. Thank you. Now I understand Kelton's question. I apologize to you, man. Sorry. All right, let's move on. Let me give you one more example, then we move on, okay?